Oke, besi ya.
Hi, everyone. We're letting people in right now. We're going to take a brief moment, and then we're going to jump into today's session. Welcome. Another minute, we're going to start rocking and rolling. Hope everyone's doing well. It looks like more and more people are joining. So I'm just going to give it another 2 minutes, and then we'll get into it. Hi, Wendy from California. Yeah, I like that, Wendy. Anyone else want to share in the next minute where everyone's coming from or calling in from? Okay, Belgium, Maryland. Okay. Oh, bonjour from Paris. Guten Tag from Germany. Hello from New York. So, all right. Well, I'm going to hop into it now. So, first of all, I wanted to thank everyone that has joined, and as we get more that is joining here in the next couple minutes, they won't miss out on a lot of stuff. But we're going to jump into so. Welcome to today's webinar. It's a Merge Alliance Microgrid Design webinar series. If you have any questions during the webinar, please type them into the chat. They'll be addressed during the presentation. A link of the recording will be sent to you as soon as it's done and available. So therefore, you guys will have a copy of that. So going to my next slide. So I wanted to introduce the panelists today. So DC Microgrids with Schneider Electric. So we wanted to personally thank Schneider Electric for being on today's call. DCIDE CurrentOS design rules we're going to cover. Some of the moderators, as you know, Dusan Berlik, the CEO of Direct Energy Partner, Kiel van den Broek, the CTO of Direct Energy Partners, and then our guest speakers is Chris Evanich, New Energy Landscape Commercial Leader for Schneider Electric, and then Avinash Papisetti. He's the Business Development and Commercial Leader for Schneider Electric. So lastly, once again, any questions that you may have, throw them into the chat. We'll address them. And I'm going to pass it over to you, Chris.
Sounds good. Well, thanks for having us today. Hello, everyone. I'm Chris with Schneider Electric, and I lead our commercial business development for North America. We have a real treat today that my colleague Avinash Papisetti, who's the Global Business Development Director for our New Energy Landscape team, is with us. And within the New Energy Landscape team, we focus on the development and on the integration of distributed energy resources through direct current. Now, Schneider Electric means different things to different people. To some, we are the electrical equipment provider who supplies breakers and distribution hardware to homes and businesses. To data centers, we provide power quality equipment like a UPS. To a factory or a hospital, we provide automation and energy management software. And to large corporations, we're their trusted energy advisor. Now, at Schneider Electric, we believe that access to energy is a basic human right. Our technologies ensure that life is on everywhere, for everyone, and at every moment. Now, Schneider Electric, we make life safe, reliable, efficient, and sustainable. And everyone is used to the way that things are. We really need to rethink our approach to energy. And the digitalization of energy has unlocked new opportunities. We've seen a decentralization of power, meaning a move away from large, central focused power plants to installing smaller generating assets that are closer to the loads. And this has created something called the prosumer. Now, in the past, there were only electrical consumers. Now that we can produce energy in addition to consuming. Now, disruptions are happening very fast. When we look back at the internet, it was just really just a curiosity, and then it became a staple of everyday life in less than a decade. And this transformation that we're seeing in the energy industry, we're seeing a lot of disruptions, but also a lot of opportunities. And there are three dimensions to the prosumer that already exist, and they're already being used to transform the new energy landscape. The first being distributed generation through microgrids. The second through decentralized energy resources. So this is using different assets and even using energy storage systems. And the third is decentralized data and control. This is through AI and machine learning. In today's conversation, we're going to focus on the technology that Schneider Electric provides for direct current applications that will help you achieve resilience, sustainability, and energy savings. And now I'm going to hand it over, I believe, to Dusan, who's going to talk a little bit here before we get into some demonstrations.
Yeah, absolutely. Chris, thank you for that great introduction, and it's great to have you and Avinash here joining us today for this webinar. Indeed, the electrical infrastructure is undergoing through a lot of changes, and companies like you are certainly going to play a key role in that energy transformation. And so today we'll look at some of the examples of how you're planning on accomplishing that. The tool that we're going to use for today's webinar is going to be called DCIDE. And DCIDE has been created by Direct Energy Partners to make sure that we can design these renewable energy microgrid systems faster and together. Designing microgrids is an extremely complex task, and we are aiming to simplify it to make it more cost effective and make sure that it's accessible to everyone on the planet going forward. Now, DCIDE has a its main focus is it has a intuitive interface. It has AI integration, collaboration, and today we will effectively build and demonstrate to you how we can design a system at the speed of thought. So let's go ahead and get into DCIDE and kick off our today's webinar session. And actually, before we start designing with DCIDE, I would like to have Avinash to talk about the CurrentOS Foundation. For various reasons, they're extremely important and key player moving DC technology forward. But also the systems that we will be designing will use CurrentOS rules. So I would like Avinash to go ahead and introduce the CurrentOS Foundation, and later on what are these CurrentOS rules.
Hey guys, thanks Dusan, thanks Chris for the nice start. So I would like to take some time to speak a bit about this foundation. This is an open non-profit foundation. So there are a lot of players, a lot of partners who are part of this foundation who have actually contributed to a seasoned set of rules. Now, as Dusan said, right, like DC distribution is not, we cannot think of it just another version of an AC distribution. It's totally different. In terms of the way the loads and sources behave, the power, the balancing, even how the circuit or products react when there is fault. It's totally a different ball game. The physics are different. So what this foundation has done is there are a lot of members like Schneider, ABB, Eaton, and even UL Solutions. So all these members, they came together, identified the good set of rules to make this DC distribution safe, efficient, scalable, like all the best know-hows from the market, and they put them in a foundation. These companies could have always thought about keeping these IPs to themselves and do by themselves, but if you don't open them in a foundation, then you will not accelerate the adoption of these rules from the greater companies, from the other companies. One of the best examples is like USB or HDMI. So when it comes to what are these rules that we are speaking about, these rules are when I'm distributing DC, what kind of products that I'm protecting the circuits are with, and if I'm protecting with a different kind of products, what is my access? So something called zoning concept. If I'm distributing DC, there is no frequency. I'm speaking about voltage. How do I use voltage to create a distributed control? Something called Droop control. So the topics like this, which are very well researched not only by us but a lot of companies and a lot of universities, has been taken into consideration and had been put into these set of rules. Any company, any players can join this foundation, become a partner. There are a set of partnerships defined, and they can get access to these set of rules. So today, these are some of the best known practices to do DC distribution. We will be using these set of rules to make architecture. Dusan has designed a brilliant architecture for one of the cases, and we will go in deep on how I'm using these rules to define this architecture and how it is making my life simpler when it comes to DC distribution. Thanks, Dusan.
Um,
Back to you.
Of course, and I just want to mention, putting my eMerge hat on here is that, the eMerge Alliance is also helping to promote the standardization and the proliferation of DC microgrids globally. And so one of the efforts that we are taking on jointly with CurrentOS is to figure out how do we create a global standard, at least between US and Europe. And so you mentioned the USB-C example, and as we are leading this new energy transformation and providing rules and guidance to the market on how to build these DC systems, it's also important to make sure that we don't make the same mistake that we did with AC, where we need to use voltage transformers between US and Europe, but that we take the best practices, from both worlds and make sure that we harmonize what makes sense. And one of those examples would be voltage levels. I think they're the most basic things to start with. And the eMerge Alliance has actually adopted the CurrentOS voltage levels in an effort to make sure that we end up standardizing globally. And that's going to benefit all manufacturers and at the end of the day, the consumers as well, by reducing the costs of equipment and making the systems more affordable. So with that said, Avinash, if you'd like to maybe touch on the CurrentOS zoning system, just so people can visualize what that is, and then we can get into the webinar.
Okay, so just to complement on what Dusan just said, we are actually foundation along with Emerge Alliance. We are actually learning from the, I won't call them mistakes, but the habits that have been put in place in AC, and how do we can improve that for DC. And as he said, like one of the best examples is this. I don't know the folks in US, Europe, other part of geography, they very well know the pain around it, right? I think Dusan is living that right now. He's in Germany and he needs to have an adapter to connect
Awful.
an AC socket. While USB-C is one of the most sold power delivery, I would say, kind of mediums today, because you go to China, you go to Europe, you go to India, you go to US, you just have the same USB-C. It doesn't change. Okay, coming down to the zoning concept. So one of the rationale why the zoning concept was introduced, because uh, if you speak to the electricians, the seasoned electricians, what do you feel about DC? Like most of them say it's scary. Like I don't want to be around when there is a DC voltage anything above 40 or 60 volts, because it can be hazardous. Now, there are you can have various kinds of protections, or you can even not have protection, have a DC bus running. Today, when we look at this new energy landscape, knowingly or unknowingly, the DC is just creeping around us. Like, you are sitting in a very room and just look around, you have DC just around you. Like, if you look at the lights, like light drivers, for example, you have your PC, which is actually powered on DC. You have your consumer electronics. So you have DC all around you. And how are you protecting? How are you using? You're actually using AC to distribute the DC, and everything around you in terms of electrical distribution is seasoned on AC but not yet on DC. So when I have a source, for example, a battery, and if I have a source, for example, a photovoltaic, if I have a DC distribution bus, if I have protection done by a fuse or done by a breaker or something advanced like ultra fast protection device like a solid state device, then how do I prepare myself to access it? And that was the rationale behind the creation of this zoning concept. Now, if you see in the zoning concept, it's very well defined in the CurrentOS set of rules. If you go deep dive, you will see zone 0, zone 1, zone 2, zone 3, zone 4. So what are these numbers? So basically what these numbers are, when it says zone 0, it is like you go into that area, you know you're going to die if you touch any metal around it. So any unprotected terminals of the batteries, even if they're in string or in parallel, this is considered to be zone 0, totally unprotected. So if you see in the design, between the converter and before the fuse, we call it zone 0. A battery terminal or fuse, we call it zone 0. This is a term, this is the area where you need to be a different level of know-how to really access it. That is zone 0. And when I protect a product or protect a DC circuit with something like a classical protection, like a fuse or a breaker, which which will save the property, but still probably for DC is not sufficient, then I come down to something called zone 1. And so in this particular area where Dusan is focusing, if you see there is a battery protected by a fuse, then it is zone 0. And then after the fuse, it is zone 1. But just after the DC-DC converter, there is you change the voltage. There's another exposed terminal. So again, you're back to zone 0. What just happened is you change the voltage levels using the DC-DC converter, but you exposed another voltage level, which is not protected yet. And that is why it comes under zone 0. So this is a brief difference between what is zone 0 and zone 1. Then comes to zone 2, and you have a lot of power electronics converters which have capabilities to limit the fault levels or limit the voltage. There is a kind of a limitation which is tied around, and that is even and it is still protected by the passive classical protection that results in my zone 2. And more above zone 2 is something that I have is zone 3. Zone 3 is nothing but this is an area where you are very well protected. You have something like ultra fast protection, which is solid state protection, where the products can trip in microseconds. So it is kind of a safe area, but you have no clue where the power flow is coming from and going towards. So it is a bus which is protected, but still there is a bidirectional flow of energy. So it's a combination of source and loads coupled to the same bus. The same zone 3, when I take down to only loads, only unidirectional loads, I categorize them as zone 4. So in zone 4, I'm very clear it is purely my loads which are connected and protected by solid state. So when I go from zone 4 to zone 0, actually what I'm doing is I'm increasing the risk factor. And based on that risk factor, what I do is I equip myself or my team when they're going to intervene a substation on an area where there is a DC bus, protected or unprotected. So this is the concept of zoning. Dutch national standards have already adopted this zoning standard because there are a lot of DC exploration happening in Netherlands, and they have very well adopted it so that the local electricians, when they are trained on DC, they are aware of this zoning protection. So you mark out, you label out zone 2, zone 3, zone 4, based on which they know how they need to access, what equipment they should be equipped with. So this is a brief about zoning. If I'm not great in technical, but guys, if you want to know more about it, feel free to reach back either through Chris or through CurrentOS Foundation, through Direct Energy Park, through Lusan. You will get more information about it.
And Avinash, there's actually a question in the Q&A, and maybe it's appropriate to address it now. Is can the current OS rules be used for medium voltage DC?
So in principle, in terms of know-how, operational philosophy, yes, but one of the rule of CurrentOS is voltage band in itself. So in terms of practices, what we are trying to tie around the low voltage distribution using CurrentOS rules, you can use them, but in terms of the behavior of the circuit in itself, it's a bit different when it comes to medium voltage. I'm not the expert in here, but I know there are certain limitations because of which you cannot exactly reuse everything which is a part of the set of rules in medium voltage. There are certain rules which has to be adapted based on the cases, based on the behavior of also the products. But in terms of Droop control, it's already been done. So you can very well use few rules. And again, there is no obligation that you need to use. There are 7 rules in general, and there is no obligation that you need to use all the 7 rules. These are kind of best practices or good practices. You can decide to use some of them which you like and not all of them.
Okay.
Interesting. Related to that, Avinash, like, so the signs, I like them in particular because indeed for electricians, installers, it's immediately clear what safety precautions or what effects they can expect. I recognize the number, the signs here, the DC sign, which I love, but like the 800 volt, what does that actually refer to?
It is based on the voltage bands that we have defined in the system specs in itself. So we potentially follow 2 voltage levels, like 350 as a nominal and 700 as a nominal. And the upper limit of this voltage, which we call over voltage band, it is tied out to a voltage level, and that is what is indicated here. It could also be what is the voltage level in that area where this zone is put up. For example, if I have batteries which are stringed up to 600 volts, could be that 600 volts. And after the converter, if it is boosting up to 700 volts, and but my over voltage band is 800, so it could be 800 volt. But again, one more point which I would like to share is CurrentOS is relatively young. It is the foundation which was created in 2021, 2022. So there are a lot of rules which keep evolving. The more people are, the more partners are jumping, the more expertise is pouring in the foundation. There is more possibility that we are kind of robustifying the rules with more know-how. So it keeps flexing. So what we speak and what we understand today, maybe it has evolved to a better version tomorrow. So please keep that in mind as well.
And one example of that would be you guys definitely adopted from Zone 2 and adopted Zone 2.1 also as more and more was known. So, but why don't we look at an actual example, an actual system that can be designed with these rules, with actual components in these zones. So we, for the interest in time, we prepared this drawing ahead of time. But Avinash, why don't you and Chris, walk us through this drawing. First of all, tell us what did you design here? Why does it make sense to do on DC? What are the benefits of this system? Let's start on a high level.
Okay, so what you guys see here is a DC distribution design specifically done for electrical vehicle. This is a product that we have launched, and as we speak is getting installed in France in our headquarters in Grenoble. So this particular if I run through the elements on the top left, you can see a product which is called active front end. It is a bidirectional converter, or we call it interlink converter. So this is the product which acts as a gateway between the AC grid and the DC microgrid. Now this product, given the size of it, can also act as a limiter for the power flow between the AC and the DC microgrid. The and what it's doing is, this is actually, if I am not wrong, it is a 50 kilowatt AFE, but it can go all the way till 100 kilowatt. And this is a 100 kilowatt gateway to a microgrid which is much bigger in size. For example, here you see there is a 50 kilowatt, which is the size of the active front end. Just on the right side, you will see the energy storage system, which is 65 kilowatt. So I have a 50 kilowatt gateway, but I have a bigger energy storage with a bigger power delivery. And if you go further down, then you will see there is electrical vehicle chargers which are connected on the DC bus, which is connected on the extended DC bus. There are 11 11 kilowatt and 6 chargers, which is summing down to approximately 66 kilowatt of power delivery, plus some auxiliary power that is for lighting in the area. So here we are using the three elements which are the core of the DC distribution, right? There is an AC-DC converter, which is bidirectional in nature, which is actually acting as a gateway of power flow into the DC microgrid. And then it is feeding the energy to the DC bus. And on the DC bus, I have coupled a multiple of energy storage cabinets. Each of them is approximately 35.5 kilowatt hour with around 9 kilowatt of power delivery. And I have stringed 9 of them, which means each of this energy storage cabinet acts independently. And how they act, on what philosophy they act, is something which I'm going to discuss and share about. And similarly, on the down, if you go further down, we have extended the bus to outside. And on outside, we have either on cable or on a busway, I have tap-offs, which are protected by the solid state breakers, which we call current routers. And each breaker is protecting EV charger, which is nothing but a DC-DC converter. So this is in a nutshell the entire concept. Now, this product doesn't have an external energy management system. This product, each and every load and source is actually running on something called Droop control. So Droop control is something which is pretty well known to a lot of institutes or a lot of companies who are doing a lot of research on DC. So just by sensing this, so the bus is at 700 volt, but as I said, right, voltage need not be at fixed number. It could be with a bandwidth. Here, we what we do is, when I say 700, the voltage level is from 640 to 760. And the voltage level inside the bus is the indicator of the health of the microgrid. So if the voltage is higher, say 701, the more the microgrid is healthy. If the voltage is lower than 700, which is say 690 volts, the microgrid is still on, but it is having a higher demand than supply. And based on this voltage level, each of the device will decide what I should be doing right now. Should I be still drawing from the microgrid, or should I reduce my drawing power so that I keep the system stable? The intent of every product is to maintain the stability in the system. So in the same way, the 9 battery chargers which are energy storage, 9 strings of energy storage put up in parallel, they did not communicate with each other. They are just working as a standalone warriors. They don't care about what other is doing. They're just like, if the voltage is 700, I am on standby. If the voltage is 710 volts, I should charge the batteries. If the voltage is 690 volts, I should discharge the batteries. The same philosophy is followed by everyone, and they act independently. The beauty of the system is, I can be in a situation where I can put down 4 strings of the 9, or I can add more strings. And on the right side, there is photovoltaic. Photovoltaic also follows the same philosophy of Droop control, which means beyond a certain limit, I just don't produce any energy. I don't feed to the grid. Otherwise, I just keep feeding to the grid. In this way, this is the real demonstration of a distributed network, where every source is independently not communicating with the other, but independently behaving what it needs to do just by sensing the voltage level. And this has been packaged in a solution, and this is what you see. And here we are doing this solution to demonstrate how it will behave for EV charging as an application. But if I remove that EV chargers and do something like HVAC, for example, lights, for example, I dim the lights based on the voltage. So you can really demonstrate on any application using the Droop control. And as I said, this is not theory. This very image that you see is getting deployed in France in the headquarters of Schneider this week. Actually, it just got dispatched from Netherlands from D system after getting tested. So it will land next week and we'll start commissioning it. The same in North America has been deployed in our site in North Carolina, in Raleigh hub of Schneider. The same design has been deployed in our Schneider China headquarters, not headquarters, one of the factories in Wuhan. So basically, this is exactly what we are living the spirit of CurrentOS, right? One set of rules, and we are trying to do demonstrate in various locations. And the good part about is we are leveraging on partnerships like with direct energy partners or with using a DCIDE. We are trying to use the same specifications but using different players. So I use the same design but use some different set of products in North America. I use the same design but use different set of products in China. So in this way, I'm taking the spirit of this open foundation of CurrentOS, but trying to deploy the same product. Um, just to dive in in this design a bit, um, as I said, there are three major elements. There is an AC/DC converter, bidirectional converter, which we call active front end, or we call it interlink converter. We have this product which is available in 50 kilowatt, 100 kilowatt, or multiples of 100 kilowatt, which I can parallel as many as them at any location. I can have three containers at three different locations on the same parking lot connected to the same bus using three different AFEs or 3 point of connections. Similarly, on the right side, you see a DC-DC converter, which is acting as a battery charger. The also advantage of this product is it has an inbuilt protection with solid state technology. So not only so that is why the voltage which you see on the bus side is kind of zone 3 for me. Um, However, if I look at the AFE, it is protected by fuse. So then the bus is no more zone 3, it is actually zone 1. But if I replace that fuse with a solid state protection, it becomes a zone 3, which means access to end user is easier. I don't need to have an electrician to access or be around that bus, physically be around that bus. That is the combination of the zoning concept with the products. On the on the bottom side of the image, you can see DC bus being extended outside. And then I have some small blue products which I call current router. These are nothing but 16 ampere solid state protection devices, and these devices are each of them is protecting one 11 kilowatt charger, which is which what you see downstream. Between the protection device and the charger, you see something called a pre-charger. So people coming from the power electronic world are very well aware of the concept of pre-charging, which is must needed. What we are doing is we have sized the pre-charger in a way that it doesn't trigger the solid state protection just because of the inrush that happens in the electronic circuit. So this is the in the nutshell. So the same as I said, these products are part of D systems by Schneider, and we deliver various applications using the same backbone in the form of DC microgrids. And if you have any kind of an inquiry or a curiosity to know more, any questions around this kind of a design or any such kind of a deployment in North America, please don't hesitate to reach out to us. Chris is your best point of contact, of course, along with Dusan and Heel here. I think I more or less covered the ground on the design. If anyone has any questions, maybe Dusan and Heel, if you have any questions, feel free.
Yeah, I actually have a lot of questions. So first of all, thank you for this very thorough overview, and definitely DC makes a lot of sense in high power applications. So DC coupled EV charging with DC coupled solar, it definitely makes a lot of sense. So you said that this entire system is controlled by Droop control, and so effectively, I think if I understood you correctly, you have a one voltage, for an entire bus, and if more energy gets put into the bus, the voltage goes up, and if too much energy gets sucked out of the bus that the system cannot support, the voltage goes down. And that's like the guiding principle and that effectively controls how the loads react to like an EV charger to make sure the bus stays stable. So I think that's fairly brilliant. But I have a question. How does that impact your wire sizing though? Is there anything special that you have to do to size the wire for that kind of a system?
Not really. In fact, what we have observed is given the advantage of DC distribution, we are actually distributing a unipolar system here. Of course, in CurrentOS, if you go, there is a future for a bipolar system where you can double the potential, higher the energy or power delivery using the same circuit. But today, what we are doing is we in technology wise, globally are yet to seasoned a lot, learn a lot on the unipolar. So it's a unipolar device. So what we have seen is given our deployments we have done in Netherlands, we have optimized a lot on copper distribution. Just because you are converting from a 4-wire system to a 2-wire system, the higher the voltage, lower the current. Also, the topic of voltage drop, when you're doing distributed source, when you divide the sources equally over a network, then you can mitigate the problem of voltage drop. And certain times, to mitigate the problem of voltage drop, people end up oversizing the copper. So what we see is actually good advantages towards the copper consumption, which is actually directly relating to carbon footprint of the system versus what we do classically in AC system.
Awesome.
So nothing
And
additional that we do.
awesome. And one hurdle that DC typically has to overcome is availability of components. And so I'm wondering that these EV chargers are they Schneider components, DC systems, or
They're from the
are they
partners.
available from somebody else?
Yeah,
Partners.
they're from the partners. So that is the spirit of CurrentOS. In the foundation, it is not only the electrical players, but we also have loads and sources manufacturers. So one of the members in the foundation is a company which is based out in Bulgaria, Ampernext, and these are the chargers who are coming from Ampernext. But again, CurrentOS is a game of system specification. So in case if there is someone out in the market who is developing a DC-DC converter for EV charging application, if they're able to follow the specifications, then we are more than welcome. They are more than welcome to join the foundation, and any company part of the foundation who's delivering a D solution can use them. That is the spirit of it. So, for example, as you pointed out, Ampernext, who's also listed out in DCIDE, for any project which has been done in CurrentOS rules, Ampernext chargers can be used. So today, D system has tested them. Schneider is using them. However, in CurrentOS, we are going to come up with a certification scheme, which will be spearheaded by UL in North America, like as a guide, but not like the only player. But similarly, a lot of players, a lot of foundation members are spearheading that in various other geographies. What the certification scheme is nothing but an open source test script which you clear and you just become qualified for you being fronted by anyone in the foundation.
Awesome. But thanks for that, Avinash. So I want to switch gears here a little bit. We actually pre-designed this system because we really want to share some exciting developments with DCIDE to the audience. Over the previous webinars, we have shown how you can actually drag and drop and design systems with the speed of thought. And like Hill was showing a second ago, you can click on an EV charger and there's a comprehensive product catalog behind DCIDE that will find you a suitable EV charger as long as it's in the product catalog and you can link it. And DCIDE was always developed to make sure that the specifications and architectures are there. We wanted to make sure that it's super easy to design a system, but we always knew that the day will come when we have to use simulations to help and size systems. So once you draw this system, the next level that's being introduced in DCIDE is to actually simulate. And the first thing that I want to show how easy it is to simulate with DCIDE is to do the power flow analysis. So here, I'm going to hand it over to you so you can kind of walk through the, how do we validate a system going forward and how do we get into simulation?
Yeah, thanks indeed. We're indeed about to share one of the latest and greatest feature that we have been working on over the past couple of weeks. So it's very excited to be with you. So DCIDE actually is becoming now a configuration tool, actually, that guides you as a designer through the design process. Simulation is one part, but at the end of the day, you can't simulate a system that won't function. So step one, if you want to run a power flow simulation, is you want to validate whether that system actually will work in that case. So on the sidebar, if you go and visit DCIDE.app, you can create a user account, and you'll notice in the latest version that we introduced validation. If you click that, it actually becomes your center where all your design rules get checked. So for instance, does every component have a voltage specified? Like I can't simulate a battery system if I don't know what voltage it is outputting. I cannot simulate a system if, like in this particular zone, for instance, I didn't specify like what the voltage that is being controlled at. So actually you can go step by step. You can design in the first place. Next, you can validate. And finally, you can simulate. But it's important to know that all your information, you're never going to leave this screen. I mean, this design evolves from the first sketch in the first brainstorm session and will get more detailed, validated, and simulated as you move towards the actual realization of your project. Fast forward a little bit. So what I did this afternoon is actually fixed all these validation rules. And then you get here. So essentially now all validation checks complete. And what you can do now, actually, you can move over to the simulation tab. And in the simulation tab, you can start a new simulation. It's done. And now you can visualize actually how the power flows into the system. So now there's about 72.5 amps drawn from the three-phase AC grid, 400 volts. DC bus is maintained at 700 volt DC. In this case, there's 71.7 amps flowing to your DC bus. There's a little bit of current flowing to power your 24 volt auxiliaries on the left-hand side. And of course, the majority of the current is used to power these 11 kW EV chargers in the system. So with the click of a button, you can actually visualize your power flows and also, like the Droop control concept that Avinash was explaining, study it and check whether actually your Droop config settings that you ended up selecting will work in practice. So to give you a little bit of an example of Droop control, so actually in the current example, I have my active front end, which is configured into constant voltage mode. So that's maintaining 700 volt. And you see my battery system is not yet active in this case because it's operating in constant current. So I just send the current set point of 0 amps to that battery. Let's say that we want to have both of these units operate in parallel and together maintain a stable 700 volt DC bus. The first approach could be that actually you say, okay, instead of configuring this converter into constant current mode, I will configure that into constant voltage mode and also set it to 700 volt DC. As soon as you do that, you'll notice actually that the validation tab warns you that actually this won't work. Why this won't work? Because there are now like effectively two voltage sources actually fighting each other in order to maintain that 700 volt DC level. That's one of the reasons why Droop control was invented many years ago, actually. So if I go into Droop control mode for both assets, you notice that I can set like a Droop resistance, which is the Droop configuration parameter, and a nominal DC voltage of 700 volt. I'm gonna set exactly the same voltage Droop settings on my DC converter. So 100 milliohm, 700 volt DC. Recall that this converter was actually delivering all the power, and this one was actually not handling any power. Let's now see how the situation changed. Okay. So you see now that actually that total output current of 72 amps is now provided by the two sources in your system. So the battery and your grid side interface converter, each contributing 50% of the total load current because their Droop resistances are equal in this case. So, and the rest of the system actually remains in the same state as we had before. So you actually see that by means of these simulations, and especially as more and more of these assets are equipped with Droop control, like the complexity increases, and you need tools like this to actually visualize and simulate how your system will perform. You're also especially interested to see like how the system performs like for a variety of operation scenarios. I mean, how does the system perform throughout the entire year? That's why we actually allow you to also conduct batch simulations. So what you can do is you can upload a CSV file, a spreadsheet essentially, with like all the operation scenarios that you want to study. Like I have a lot of solar output, I have zero solar output, I have a lot of demand, low demand, etc. You can actually download a template file, upload it again, and then actually the IDE will simulate all these scenarios for you, and you can analyze them step by step without running these simulations thousands and thousands of times repeatedly. And this is all a step towards helping you to actually validate your design, because that's what you want to know at the end of the day. Is this going to work? And especially, are there cases where my system is not going to work? And how do I go about that? How do I fix it in that case? So that concludes the simulation part.
And all this is accessible through a web browser.
True. True.
So I know I'm a little bit biased, but when we did internal testing, I think there were two things that were very impressive. One of them was that you could just copy and paste your design and just run a new simulation. So literally, as you're building the system at the speed of thought, you're also building your simulation. And the second thing that was the most impressive is when we unleashed the simulation model, it got unleashed on all your previous drawings before. So all of a sudden, the concept drawings that you had have also become much smarter. And I think this is a concept that we'll continue to explore going forward to help and make sure that we can design systems at the speed of thought and validate them, help size systems, wires and system sizes going forward. So this is just the start, but it already shows the power of this simple yet intuitive system design. Right. Well, thanks. Go ahead.
Then there's one more thing, actually.
Aha. There is one more thing.
We already talked a lot about the CurrentOS validation rules in there, but to us it is very important that you never have to actually leave your design. When you're mentally actually designing a system, you want to stay here, you want to be creative, you want to draw different system architectures, you want to validate, you want to simulate, Draw at the speed of thought means also access information at your fingertips. So Dusan, you ran a little experiment actually last couple of days that I want to share.
I did.
So actually we have our Ask AI, and we have the latest system reference document of CurrentOS. So
Which explains all the rules and zonings, and I have a hand copy of it here that you could read and study, or you could leverage AI to help you, for example, explain the CurrentOS zoning concept. And this theme, as you go through our product catalog, if you see the badge of AI enabled, you'll be able to actually talk to your components and designs and documents. So as a systems engineer or designer, you get the information when you need it at your fingertips. And so the you can see that the AI is summarizing very quickly what are the zoning concepts, how many are there, and just giving you the bullet points. Now, here, what if you wanted to know what is the minimum maximum voltage for a 300-volt DC system? Where would you find that? So this conciseness is what we are building into the system to make sure that it really just tells you the numbers when you need them effectively. And one thing that the CurrentOS system reference document I know is really adamant about are the different grounding concepts, because the grounding concepts are the ones that really determine your protection, or like the basis of the entire system. And if you do want to find out what are the approved earthing concepts to help you with the design, you can just effectively ask AI. So it looks like the TNS earthing system is supported. What is a TNS earthing system for the people in US?
let me ask.
Oh, okay. I mean, I guess we could replace you with AI too. That's okay. Yeah. So if you want to clarify some concepts or find something in a document, this is really a fantastic way to do the design, and everything has a reference. So if you click on a link, the link will take you straight to the document, so you can verify exactly where the information came from. Well, thanks for that, Gil. So we have a few minutes left. I think we can look through some of the open questions that we have from the audience. So there's a question. I think this is good for Avinash. It says that, are the loads connected using FMP considered zone 4 protection in CurrentOS?
So no, it's two different topics when it comes to the FMPS and also the Zone 4. I'm not very well, apologies, but I'm not well versed on the topic of FMPS, but what I know is it is not connected. It's two different technologies altogether. Again, Zone 4 is just the mapping of an area in your substation, for example. FMPS is the technology in itself. Zone 4 is not the technology. It is like you're creating a zone 4 because of a particular technology that you're using to protect your bus. This is what I can say. But with my limited knowledge on FMPS, I can tell you that probably if we are using FMPS to protect the distribution downstream, probably it can lead to a zone 4 system. But honestly, I'm not the best to explain this.
Okay. Yeah. Well, they can always follow up with you, and you can help them
Exactly.
figure and answer the questions. Thank you for that. There's two more questions. One was is fault current also linked to zones?
Yes. The
Okay.
fault current is link, and that is where the demarcation between zone 2, zone 3 comes into picture.
Okay. Okay. And we have one more question here from Brian, and I think this is with regards to the Droop control here. It says, does this mean you set the priority of source choices by setting different Droop resistance values?
Exactly. That is the beauty of the Droop. And imagine you have an office, you have 3 parking slots which are on DC distribution. You can actually set a different priority for the customer and the visitor and your employee, which means at the same voltage level, there is a possibility that you can charge 3 different cars at the 3 different speeds just because you have marked a different set point inside the product for the same voltage level, the priority set point, exactly what you're sharing the screen. So the slope of the curve can be updated based on which you can decide on the priority, and also the set point of where the charging, discharging, or where the transitions will start. This also can be updated. So that's the beauty of the system. Not only it can be done between various loads, it can also be done between various sources, and it can be done under various loads and sources. So
Okay.
using this philosophy, you can evaluate and evolve various kind of applications, critical, non-critical, etc.
Okay. And last question, and we have to close to be respectful of everybody's time, but I just came in. How many projects are already realized of DC microgrids in the US, France, China, and industries? Can you ballpark it?
A lot, a lot. Uh, in last 3 years, in fact, if you ask me which country has deployed the largest number of DC projects, I would rank China as first.
Mhm.
Because there is a state-run initiative in China called PEDF, which actually kind of gives advantages, benefits to various communities or companies if they are realizing DC distribution. You can Google out PDF and you'll find more data about this particular concept. P actually stands for photovoltaic energy storage, D for DC, and F for flexibility. And then in Europe and North America, we are not very far behind. Actually, we are also deploying a lot of pilots, a lot of companies. They are getting more and more closer to DC technology. So I cannot give a ballpark number, but I can tell you that every lot of companies, the legacy player, even some new players are deploying DC distribution as a microgrid or even not as a microgrid as we know it.
Okay. Well, Avinash, thank you so much, for participating today, and same with Chris. I'm gonna hand it over to Matt to do the final housekeeping items for today.
Thank you.
All right. Well, that was something else, huh? That was amazing. I was over here, my jaw hit the ground. So needless to say, I put a bunch of links in the comment section in the chat. So feel free to email us at info@Direct Energy Partners if you need to discuss more about DCIDE, or get in touch with Avinash and Chris, or RE Plus, or let alone Emerge Alliance. But once again, here's our link to start designing with us. When you're actually in DCIDE, go on the top right. Once you're finally logged in, there is a plan section. We are releasing that beta feature that you saw for the power flow simulation. It is at a limited seats right now because we don't want to rush it, but it's kind of first come, first serve. And then that's also going to put you at a spot where any advancements to DCIDE, you have first action with. So any questions around plans, getting your team involved, you can contact me at sales@directenergypartner.com, or go ahead and request a feedback or something within the app. But needless to say, upcoming events with the Emerge Alliance, there's going to be another webinar for the Electric Avenue series on June 18th and July 24th. Our next microgrid design series is going to be June 26th and July 10th. Go ahead and register for those events at emergealliance.org/events. Emerge Alliance is hitting the road. They're going to be at RE Plus event in Philadelphia. So they're going to have an exhibit, business lab in session. So come on and stop by. They'll be in Anaheim from September 9th through the 12th. 2 live microgrids are going to be in place. 2 pre-conference microgrid workshops, 30 grid edge theater education sessions, and the RE Plus technology as well. So you can visit RE Plus or RE-Plus.events to get signed up for any of their upcoming events. We'd love to see you all there. And then lastly, from what Dusan mentioned about Emerge Alliance, you know, there's help setting the standards for DC and AC hybrid systems. Feel free to join up and become a member at emergealliance.org/join. And then most importantly, we want to thank Chris Evanich, you know, with Schneider Electric, you know, of course, Emerge Alliance, RE Plus, for allowing us to put this webinar series together, and of course, Dusan and Heel for your ever vast knowledge with everything. So for now, I'm going to close out the session, and we will see you guys very soon. Take care, and we'll talk soon.
Thank you.
Thank you.
Thank
you,
you,
everyone.
all. Bye.